Okay, so it's my great pleasure to be here, and thanks for the invitation. Yeah, so it's about I'm going to just talk about unitary ensemble, unitary invariant ensemble, and where the potential is now slightly different than usual, where I'm going to change the potential to be locally varying and see what happens. Right, so I'm going to start from the beginning. Okay, so here's the familiar unitary invariant ensemble with a Vandermonde square, and usually we have e to the minus nv of x. Okay, so the v is the potential, and then we know many things like the density of states is given by equilibrium measure, and the reason that I put n there is so that for general class of potential v, the eigenvalues sit in the finite part of the real line, right? So that's the reason that we usually put n there, and then these eigenvalues form the determinantal point process, and so then we have the bulk universality. For example, if we take x naught to be a point where such that the equilibrium measure does not vanish, then around that point, because it's eigenvalues are in a finite interval, the typical spacing between eigenvalues is 1 over n. So if you take that scaling 1 over n up to that equilibrium measure, then there is universality, meaning that right. So these eigenvalues form a point determinantal point process. So there's a kernel in the background. That kernel converges to the universal kernel given by the sign kernel. Right. So this is a well-known part. And then the S is given explicitly in terms of the sign kernel. It's proven by many groups, Postgen, Chobina, and Blair and its, and David Krikova, McLaughlin, and Benakis and Zhu in late 1990s. And Lubinsky come up with a different method in mid 2000. And more recently, Bogart and Ardash and Yao gave a different technique, especially for the general beta in this case. In all this description, the V is usually taken to be macroscopic compared to the local spacings of typical eigenvalues. Right? So what I mean by that is that if this is a potential times n, and these are the eigenvalues, if you zoom in, then the spacing between the eigenvalues is 1 over n, and the height of this potential, n times v, changes like a v prime times y, right? Because here's n there, and the spacing between the eigenvalues is a and a plus y over n. So by Taylor series, it's typically constant times y. So locally linear, n times v looks like a locally linear. Okay? So what I was curious about is, well, what happens if you change the potential so that it looks wiggly, even locally? Okay, what can you say about that? Okay? So for example, in the spacings of the eigenvalues is 1 over n, and this is a little bit wide. Okay, so then, of course, we don't expect the universality anymore because the potential should influence the eigenvalues all the way in the small scaling. But can you say something explicit about that? Okay, so that's the question. So for example, if you have nv and you just add cosine in this fast variable nx, okay? Or more generally, n times v1 of x plus a vt of nx, where vt is a continuous and bounded function, as an example. Or you can have a mixed scaling. So here's n of v of x, and then here's cosine of now lambda. Lambda is another scaling. So n over lambda cosine lambda of x. Yes?
Is this pure mathematical curiosity, or are there some applications?
Well, so I'll give you motivation a little bit later. Yeah. Right. So yeah. So here's n over lambda and the cosine lambda of x. Then it becomes, if you take a derivative, then lambda come out and cancel out. And if x is 1 over x, 1 over n scale, then this will be order 1 in the local eigenvalue scaling. Right. So n over lambda is the correct scaling you have to put. So if this n over lambda is just too big, maybe this wiggling is just too much, then the potential is just too strong, and then you won't see sign kernel anymore. Everything is just determined by this potential. If this wiggling is too weak, then everything should be almost like a sign kernel. The potential should disappear. And maybe this is the right scaling to see the effect of both sign kernel and the local varying part of the potential. Okay. Right. So that's the general structure. And you can say, is there a density of states, first of all, and how is the sign kernel going to be changed? Well, for the model that I introduced, I cannot say anything. But if you change the problem to circular version, it becomes much, much easier, and the math is actually too easy, but it's a little bit cute, so I just want to talk about that. I want to talk about the case when especially the V1 is not there, and we just have this part. Okay? And also we can talk about the Jacobi version of that, which can be obtained from the circular version. So here, so before I say the motivation, here's a circular ensemble with periodic potential. So just to state the matter. So there are two parameters, right? N and lambda. N is the number of particles, and lambda is the period of the background potential, and background potential is periodic with it's highly periodic, okay? Highly oscillatory. Right? And the unitary, these eigenvalues come from the density function come from the eigenvalues of unitary group, where you put the density function like this on the unitary group. You can arrive there. For example, if V is like a minus cosine of n theta, then this will be your potential. Okay, so it's a highly periodic potential in the background, and you would like to know what happens to the eigenvalues given by that. Okay. Right. So here's a pseudo motivation for me. So Rao and Rogers in 2005 measured the gaps, the spacing between the parked cars on the street in London. So on the London street there are long streets without any driveways, and maybe there are 20 cars can park as a parallelly parked, and then you measure the distance between the parked cars. It's fully parked, right? So there is no empty space, and a new car cannot go in. So measured in the middle of the night, and so this is the data that they obtained. So they compared this one against the standard parking model. Standard parking model is people have taken that as the model of random interval filling problem of Rennie in 1958. That's what has been like a standard parking model somehow. So that model is defined as follows. You take a long interval, like a line, and then you have a needle of size 1, and you drop it randomly, uniformly in that interval. You just drop one, and then you drop the second one, and uniformly in the remaining place, so that it does not overlap the existing needle, and so on, until you fill the whole. You cannot put any more needle. Okay, so that's the model, and then you take this the initial interval to infinity. So you're filling the whole interval, whole real line. Okay. Then of course, if you do that, then there is no repulsion between these needles, right? So the needles can come really, really close, and of course, so there's the if you look at the gap size distribution between the cars, and there is a non-vanishing density at 0, okay? Unlike the vanishing density at the origin. Okay? So that's natural, but this model has been used to model the parked cars. It can be useful for other observables of the parked cars, but not this particularly. This is a gap distribution. Okay? So that was a conclusion of Rao and Rogers' paper. Okay? So it's not consistent with the standard parking model.
It's because cars repel.
Yeah. So yes, cars repel, right? Of course, right? We know that, right? Yeah. Well, unless you're, I don't know, in Paris and can be arbitrarily close, but yeah. So yeah, and then the Rao and Rogers try to introduce some other Markov models to explain this repulsion. Okay, but because there was repulsion, there's another paper by Abel and Margot in 2006. Maybe this looks like a GUE. Okay, maybe. Okay, so that's the whole content of this paper. Right. So of course, Peter Seva, who worked on this bus problem in Cuernavaca, looked at this problem and collected data in Czech Republic, and he used the high school students to collect the data and then analyze it. And he got some mixed results. I mean, sometimes if you have a car parked on the right side of the street, and that looks like a GUE, but if it's on the left-hand side, it looks like a GOE instead. So it's not, I'm not quite sure whether random matrix is actually a right model or not. I don't know. And Peter Seva himself proposed different Markov model. Random matrix is you are given these eigenvalues simultaneously, but Markov model is you put one car at a time, right? So that's different nature. But anyhow, So around the same time, I had a under resistance Anthony Fader, and I asked him to do the same measurement on the street in Ann Arbor, Michigan. But there was one big problem. I mean, immediately he tried to measure. So he was undergraduate student, and he brought the ruler, and he brought his girlfriend, and then on the street, and he measured the data. So it's Midwest, right? So every street has driveways. So there's no long street that you can have 20 cars parked without any interruption. The only long street there was had parking meters along the way. Okay, and then he could measure the data from there. But of course, because of parking meter, it will be completely different. It's not GE anymore. So he tried to fit this with other beta ensemble. There was this What is Beta website by the student of Alan Edelman. So he put the numbers there, and then it gives you what's your beta number. The beta comes out to be like a 9 or 10, meaning they need higher repulsion than the beta 2. Okay, and also he could do something from parking garage, but there are also the markings on the parking garage that your car should be in this rectangle, and that gives extra repulsion. Okay, so but maybe parking meters are periodic potential, and then if you try to model this one with if you decide to model this random matrix model, then maybe parking meters are periodic potential, and that should be your model. Okay, but this is sort of pseudo, right? Okay. Right. Okay. So that's my motivation to think about this problem. And for the circular case, I said that we can write down the kernel very explicitly. Everything is very, very easy. But I asked a few people, but people didn't seem to know that fact. But I forgot to ask Peter Forrester. Okay, of course, I posted my paper. Peter sent me an email. Well, I've done this, 20 years ago, right? With some part of it. So what Peter did was he took the lambda and n to be the same. So exactly one period per eigenvalue, and he computed free energy and 1-point and 2-point correlation function explicitly for beta 1, 2, and 4. And his motivation there was the crossless and threadless conducting insulating phase transition. So that's basically 2D Coulomb charge with periodic background so that the charges do not collide. But he wanted to have a version of that where we have only one compound charges, right? Just all the charges are say minus, and the everything. Then you give the background the periodic potential, and by changing the temperature, maybe one can see kind of transition there. He computed beta 1 to 4, and then based on that, he extrapolated the result, and then he have a conjecture for beta, general beta for free energy. Okay? And then using that, based on your phase transition point will depend on potential, but basically beta equals 2, that seems to be the phase transition temperature. So that's still an unanswered problem, whether we can actually see that for general beta. All right. So let me just now go back to this model and try to say what one can prove. Right. So model is now circular ensemble with periodic potential. So here's a Van der Waals square, and now there are two parameters n and lambda, number of eigenvalues, and 2 pi over lambda is a period. Okay. So higher lambda means the potential has higher period. Okay. Of course, this potential is invariant under this change shift 2 pi over lambda, and the Van der Waals term does not change by the simultaneous shift of the eigenvalues. So the whole system is invariant under this change of variable if you shift them all together. So therefore, the density of states should be periodic with period 2 pi over lambda. And the underlying determinant point process has the kernel, which is also invariant under this simultaneous shift. Okay. So the problem is now simple. I mean, this is the beauty of a Gaudian meta method that gives you the way to solve this one if you solve one particular problem. If you solve the orthogonal polynomial problem, then you are done. Right? So determinant point process structure tells us that all the correlation functions are given by this kernel, where the kernel is built out of the nth orthogonal polynomials with respect to the underlying measure. Underlying measure has the structure that potential of e to the I lambda theta d theta. Right? So the underlying measure is potential is periodic. And the kernel is built out of the nth orthogonal polynomial. Okay, unlike the the Hermitian case, we only need the nth orthogonal polynomial instead of n and n minus 1. Okay, that makes things simpler somehow. And times this the usual potential term. So the question is now, well, what do you know about this orthogonal polynomial with respect to this periodic weight? So here's a very simple lemma. So if you have a weight, base weight W, and the periodized weight e to the I lambda theta, and look at the orthogonal polynomial with respect to that one, and put this superindex lambda. And if you look at nth orthogonal polynomial, with respect to n periodic potential, you can reduce to pi 1, the first orthogonal polynomial computed as e to the n. Okay, so this should be a orthogonal polynomial of degree n. So polynomial of degree n. This one is now pi 1 is polynomial of degree 1, the linear. You put z to the n, so it becomes n polynomial of degree n. It's a simple fact that this is polynomial of degree n, and we can just check that this is orthogonal with respect to all the lower order terms with respect to this weight. Okay. More generally, if you have the bn plus c for orthogonal polynomial and the period is an, then you have another simple relation. Okay, so basically you have to just change a variable. That's very, very simple.
This has a standard name.
It has a name. Yeah.
I'm looking it up. I don't remember it. I'm getting old.
Right. Okay, so that means that if you have nth orthogonal polynomial, you can reduce to the first orthogonal polynomial. The degree of the orthogonal polynomial is the number of particles. So if you have n particle and the lambda period system, there is a simple relation to the one particle and lambda over n period system. Okay, so if you have n and lambda the same, if you have one particle per potential, I mean there is one period per particle, then you can change it to just one particle system problem, restricted on that smaller potential. Okay? And when a period of lambda is integer. If it's the other way around, then you can make it one period and a small number particle system. Okay. So let me go back to here and then start the result. Okay. So so density of states. So this potential now can be thought as interpolating of two particular situations. When lambda equals 1, then this whole weight is e to the minus n v of e to the I theta. So that's usual external potential problem. And when lambda equals infinity, right? So formally, if n is fixed and lambda is infinity, then this becomes 1. So the whole weight is 1. So you have CUE, the circular unitary ensemble. Okay? So you are interpolating the circular unitary ensemble to the general external potential problem. So lambda equals 1, the density of states converges to the equilibrium measure. And lambda equals infinity, density of states for the CUE, circular ensemble with background potential 1. So just 1. Okay, uniformly distributed on the circle.
Sorry, just to clarify, is lambda real for you or integer?
Lambda is integer here.
Always integer.
Yeah.
And is it commensurate with n always? Or
So I'm going to take the lambda over n is an integer, or n over lambda is integer. But one can make the lambda over n is rational, but it's hard to describe. So I'm not going to talk about that here. Oh, okay. Good. Yeah. So I also forgot to ask another person. Okay. Right. So in between there is now background wiggling potential, and then does the density of states converge to something. Okay. In general, it doesn't converge, but it's still bounded if you take this prefactor n over as n over lambda. If you change to something else, it may not. Okay. So here's a first result. So I'm going to distinguish two cases when n is bigger than lambda and n is smaller than lambda. Two possibilities. So first, n is bigger than lambda. So n is bigger than lambda means that so n is k times lambda, k is integer. So per potential, there are k particles, right? So per period. So the potential is now periodic with period lambda. Okay, and then that will divide the whole circle into lambda sub-arcs. And one arc, on average, there will be k eigenvalues. So then the density of states for that small part is given by the density of states for the k particle system with the weight e to the kv. So when k becomes infinity, so that means when k becomes infinity means that per period there are more and more particles, right? So then the whole system looks like the larger system. So then the whole thing should go to the equilibrium measure. Well, I mean, not only when n is lambda and n are of the same order, but even lambda tends to infinity, but n is much larger than lambda, then we still have the same story. Especially when n and lambda are the same, and from here when k equals 1, so that means that there is a 1 particle per period. Okay. So then the equilibrium measure for the 1 particle system is simply the potential, because there is no Vandermonde anymore. So in that case, everything is just proportional to the external potential. Okay, so let me just see the picture here. So density of states will look like this, right? So here's a periodic equilibrium measure. That's the density of state. Density of state is periodic. This is, the lambda is a period. And sometimes it looks like when n is bigger than lambda, there are these equilibrium measure structure, but still it's highly periodic. On the other hand, when lambda is bigger than n, okay, so the potential changes faster than the number of eigenvalues. So for one eigenvalue, there are a lot of period. Okay, so that's the next case. Then everything will depend just on the potential. Okay, so basically the sign, the other part doesn't appear. And especially when k tends to infinity, and this whole thing goes to 1, so the right-hand side goes to 1, that is consistent with the CUE case. Okay, so summarizing it, so we arrive at the following thing. Right, so when n is much bigger than lambda, everything looks like an equilibrium measure of the background potential V. Well, that happens when lambda equals 1, but not only that, and n is much bigger than lambda, it is still the case. When n is proportional to lambda with the multiplicity k, right? So then the density of states will be just same as the k particle system. And when the lambda is bigger than n, but a multiple of n by k, then we'll just have the potential as a density of states. And finally, when n is much smaller than lambda, then everything will go to the circular case. Okay, so that's the density of states. And then the bulk scaling limit is how the sign kernel is going to be changed. Okay, so then again, there are two special cases when lambda equals 1 and lambda is infinity. So lambda, let me say this one first. When lambda equals infinity, that's the circular ensemble case. So therefore, the kernel, the k-point correlation function, I'm sorry, the kernel for the determinant point process converges to the sign kernel if you use the 1 of n scaling. On the other hand, when the lambda equals 1, then the problem is when lambda equals 1, then you have e to the n v of e to the I theta. Then that's usually the external potential problem. So then there is a background equilibrium measure depending on your potential v. And if your point A is such that the equilibrium measure does not vanish, then you still have the sign kernel. So in both cases, you'll have sign kernels. Right? But with different scaling. I mean, so if you scale different scaling, so if I change them to the same scaling, left-hand side, then the right-hand side will depend on your equilibrium measure. Okay? So at one point, we have the sign kernel, and the other point, you have your sign kernel, but slightly adjusted depending on your equilibrium measure. Okay? So there is a sign kernel and sign kernel in both extreme, and then something will happen in between. Okay, so this is what happens in between. So the when n is bigger than lambda, okay, there are more particles than the period. We'll have the sine kernel, but scaled by 1 over k, and then the kk, which is the kernel for the k by k system. Okay, the k by k system for the external potential V. So when k tends to infinity, one should arrive to 1. But when k tends to infinity, the V becomes S00. That's 1. So this one will go to 1. But now this part, the kernel for the k particle system will converge to the kernel for the infinite particle system, which will be the sine kernel. Okay, so the right-hand side will go to sine kernel. This will go to 1. On the other hand, when lambda is bigger than n, and then by the proportion k, then we'll just have the sine kernel is multiplied by this potential. Okay. So especially when n and lambda are the same, the one particle per period, we'll just have e to the potential part. So the sine kernel is just simply multiplied by the potential, and that's the effect of the local potential in the local regime. Okay. So the sine kernel will be, so you'll have a stronger repulsion than the usual sine kernel. All right, so if I plot the graph, so this is a graph of 2-point function, so R2 of 0 and x. So computed at 0 and x, so that should be sort of, if you have a point particle at 0, and what's the probability that you'll have another particle at x? So in the circular unitary ensemble case, this is the equilibrium measure, and this is the plot of R2. So it has high point at 1 and 2 and so on, so to indicate that it's more likely that you have another particle at length 1 and length 2 and length 3 and so on. Okay. But if you have other potential like this, so if your V is like this, say cosine potential, and say n and lambda are the same, then the blue curve is going to be the equilibrium measure. So equilibrium measure density of states does not converge to any constant function, but itself is wiggly. And then that is synchronized with the sine kernel, the maximum, exactly at the same point. So the 2-point function will have a stronger height difference. So that means that you will have a stronger repulsion than before. Okay. And this is for the n is 2 lambda case, and this is n is 1 over lambda case, and n is 2 lambda. So then you'll have more likely at the position 2 and 4, but you may want to go to position 1 because that is the effect from the sine kernel. So potential tells you that you should go to 2 and 4, but the sine kernel will try to tell you that, well, you should go to 1. Okay. So there are the competing effect between these two things. Okay, so however, if you change the scaling differently, then you may have a different effect. So if you have so here I take n over lambda, but if you just take n to remove lambda, right? So then the effect of the local potential is much stronger. Okay, so in this case, the locally the potential looks like infinity everywhere. And that's exactly what happens if you work out this part. So when the potential is say the cosine, and the potential is the equilibrium measure does not converge to anything, it's either 0 or infinite, depending on whether your potential your angle is 0 or a multiple of 2 pi. Whether it's multiple of 2 pi over n or not, it's either is high peak, infinite peak, and then 0 and infinite peak, and 0 and so on. Okay? But to have a nice bounded equilibrium measure, you have to make a proper scaling. Okay, so here's a Jacobi version of that problem. Okay, so this will give us the hard edge. So Jacobi case is now this is a Jacobi ensemble, the Van der Waals square and the times 1 over root 1 minus x squared. So here's the density of states given by 1 over root 1 minus x squared. Okay. So then how are you going to change this? So if I put arbitrary periodic potential up there, so again, I don't know how to do that, but for a very specific perturbation, periodic perturbation, we can work this out using the results from the circular ensemble. So let Tk be the Chebyshev polynomial of first kind. Okay, so that's cosine of k theta when x is cosine theta. Okay, so that's the standard Chebyshev polynomial of first kind. And so here's the, I think this is k equals 9 and 10 and 11. Okay, so it's kind of periodic, but more dense near the boundary, minus 1 and 1. Okay, so think about the following potential. So here's potential here. So here's Jacobi, but now we change it to e to the minus n over lambda. And potential now the argument that I'm going to put is the Chebyshev of degree lambda. Okay, right. So then so for example, if we take v to be this kind of a 5-degree polynomial, and then the blue curve, which is Jacobi weight, is going to be changed to this more wiggly curve. And then the question is now, what happens to, what's the effect of these local oscillations to the eigenvalues? Okay, so for simplicity, I'm going to take n and lambda the same. So the period and the eigenvalue are the same. And then the density of states, it change the structure. The density of states will look like some explicit constants a and b times the Chebyshev polynomial and times the potential term. Okay, and then the bulk scaling limit, well, for some sequence x naught of depends on n, so that sequence is chosen so that I'm going to look around the origin, but as n changes, it may be the local minimum or local maximum. So I'm going to keep track of which one that I'm going to talk. So I'm going to keep track about around the local maximum near the origin. Okay, I'm going to zoom around that point. So that's a little bit of technicality. And then scale in the usual way of on of n. Then one gets sine kernel plus some extra term. Okay, so these are structure changes from the unitary case. So it seems that maybe there's a due to of the putting the potential in a different way. That I'm not completely sure at this point. Okay, but the structure of the previously it was sine kernel times the potential part, or sine kernel times some other structure. But now the sine kernel has added perturbation. Okay, and then there is a potential specific term. But the same structure will be present for the hard edge. So for the hard edge, so for the Jacobi unitary ensemble, near the hard edge, the scaling is 1 of n squared. So that's the hard edge scaling. So 1 of n squared scaling, and then that goes to the Bessel kernel. The Bessel especially minus 1 over 2. Okay, given by these Bessel functions. Right, so the eigenvalues have scaling near the boundary 1, because that goes to infinity. Density of states go to infinity, so we have to adjust the scaling, which turned out to be 1 over n squared is right scaling. But that's the standard result. And if you add the locally varying potential term like this, and take the lambda and the same, and in that case, the hard edge structure changes to the following. So here's a Bessel kernel, and plus another kernel L. Okay, it's a linear combination between these two things where A, B are explicit. The L has this, again, sine minus sine structure, but changes a little bit, and times the potential specific term. Okay, I think I ran everything just too fast. So, okay, it's already a summary. So, okay, so yeah, so we looked at the locally varying potential. So when the potential is not the usual type nv, but added by the another scaling, v of lambda n2, or n over lambda times v of lambda x. And for the circular case and Jacobi case, one can compute those things explicitly. Okay, so in the circular case, especially if you drop this V1, if you add V1, I don't know what's going to happen. But if you just look at the V2 term, that's the circular ensemble with highly periodic potential, then using a simple relation between the orthogonal polynomials of the usual potential and the periodic potential, one can write down the kernel explicitly. And that gives the bulk scaling limit with the determinate points process with the kernel structure given by the sine kernel times so multiplied by another kernel. For the Jacobi unitary case, with the potential changes to V times Chebyshev polynomial, and then the structure is just disrupted, you get a different structure, and then one can get the bulk and also hard edge limit. And of course, one can ask the same question for other beta 1 to 1 and 4, and especially general beta. Okay, that was the original motivation of Peter Forrester. And also, this is only for the Jacobian unitary case, and one would like to know something about Hermitian and the Laguerre case. Okay, that's I'm not completely sure. And also, because we are only considering Jacobi, we have hard edge, but we don't have soft edge. So if you have Hermitian case, then probably we'll get the soft edge, and Airy kernel will be changed to something else. Okay, I don't know what that exactly at this time. Okay, so I'll stop here. Okay. Thank you so much.
So, what's the moral for the cars in London?
Yeah, so so that's well, I don't know the moral for the cars in London, but